So, as I said, the title of this webinar is Latest Developments for Simulation Model Assembly and Management of Iterations. A while ago in ANSA, we introduced the modular environment for the effective handling of modular runs. The key features of this environment include the breakdown of the models to their base modules in order to tackle the increasing model complexity, the use of smart assembly tools for the efficient assembly of the models, the reusability of data and modules across different model and load case variants, and finally, transparency in the relationships between data in order to offer full traceability across all levels. Now to this, if we add the dimension of time, so if we look at the timeline of a model within a project, the modular environment also offers effective creation of run iterations without the need to load the full models, validation of the assembly integrity after the creation of new iterations, traceability between the changes that were introduced in the models and their impact on simulation results. During this webinar, we will review some of the latest developments in the area of modular run management, focusing on the simulation model assembly and the management of iterations. Let's get started with the modular model assembly. In the typical simulation model anatomy, the model consists of the base modules called subsystems, and these contain the geometry of each subassembly and the internal connections that bring the parts of the subsystem together. But they also contain another integral definition, which is the marking of interfaces at subsystem level. This is the locations or the points where the various modules will be assembled with their neighbors. A special subtype of subsystems, called connecting, is used to manage the intermodular connections, which may be either connector entities or plane connections, and in some cases, entities called assembly sets that are used to collect interface sets from the base modules. When it comes to the use of intermodular connectors, the assembly is performed using the base module interfaces, so there is no need to load the full representation of the base modules. Their interfaces are loaded, and then connector entities can be created in order to generate the connecting elements. In the modular environment, the interfaces required for the creation of the connecting elements are tracked, allowing ANSA to evaluate the compatibility of new module iterations and enable the reuse of existing connecting subsystems between models. On the other hand, a key request from our users has been to facilitate the use of plane connection entities like adhesive lines or spot welds in order to connect two subsystems and still be able to validate the assembly and update the model without loading the full representation of the base modules. In the latest ANSA versions, the smart assembly methodology that we employ in the modular environment has been enhanced in order to support the use of plane connection entities for intermodular assembly. We will see together during this webinar how ANSA can now detect if modifications in the subsystem affect the endpoints of connections in the connecting subsystems, and identify whether the solver file of an existing connecting subsystem can be reused or whether its connections must be reapplied so that a new iteration is saved. Moving on, in the modular environment, each model container has a process that must be followed in order to verify that it's ready to be saved in the data repository and that it meets the requirements of its parent container for the composition of the model. Different build processes are offered for each model container. For example, we have different processes for parts, different processes, build processes for subsystems or simulation models, so that the relevant actions are taken for each model container in order to ensure the validity and the integrity of the models. This build process can be triggered automatically from save. So when you trigger the save action for a subsystem, for example, if the build process fails, then save can be halted, preventing the saving of invalid data. On the other hand, If the build process is successfully executed, then the ANSA definition file of the subsystem is saved in DM, and the reference in the data manager is created between the build process that was used to produce the ANSA file and the subsystem itself. When the solver keyword file of a subsystem is saved in DM, then a relationship is created in the data manager, and the relationship between the ANSA and the solver file is captured and stored as metadata in DM. Now, let's move on to an overview of the latest developments in the management of model iterations. In the modular environment, the creation of new model iterations becomes a seamless task. So starting from a solver keyword file in the storage, for which updates need to be introduced, and performing the next iteration action, the system can trace the references and load the ANSA definition file and the respective build process metadata in the preprocessor. Various modifications can be performed, and then a new iteration of the subsystem can be saved in DM, which of course will be validated with the same build process as its parent. And then, when these are saved as a new iteration, a new lifecycle reference will be created between the two iterations. A key question that comes from our users at this stage is how to trace the model modifications between subsystem iterations in order to associate them with the effect that they may bring in the simulation results. And this is again something that we will cover during this webinar. To address this need, we have introduced change set management functionality in the modular environment. This tracking of modification results in the creation of a change set, which is an ANSA entity that contains all the actions and parameters that were applied on a module, and then this is stored as metadata in the system together with a new iteration of the subsystem. We will see in this webinar how this change set can be used to quickly visualize the life cycle of a simulation model and get information on who did a change, when, and what was modified. Moreover, we will have a look at how the comparison between models can be performed in ANSA with functionality that compares the simulation model both in terms of metadata as well as in terms of the contents. Finally, we will also have a look at one of the latest developments, a report generator, a report generator that collects all the available information for a simulation model in terms of identity, attributes, contents, lifecycle, and references, as well as a changelog from its parent. This is presented in a clear and organized manner, allowing the user to make better sense of the data, identify modifications between different base module versions and the model variants, and understand the impact that this brings to the simulation results. So, without further delay, we can now proceed to the live demonstration of this webinar. So, this is the model that we will be using during this webinar. It's a reduced simulation model where we have a section, a part of the body-in-white subsystem. So this is the sub-assembly that you can see in the gray color. We have a glazing subsystem, the front windshield that you can see here. And then we have the front left-hand side door and the front right-hand side door. So this is an overview of the model. This is what we will be studying during this live demonstration. And let's see how in the modular environment, a user can start building such a simulation model and creating new iterations and understand the various modifications that take place. So let me quit this ANSA session. So I will start with a new ANSA session, a new empty ANSA session. I am connected from the DM functionality to a DM. Okay. This is currently an empty DM, so if we browse the contents, nothing is stored in the data manager. And we'll start saving our base modules. So I will open first the database for the body-in-white subsystem. So let's review the contents of this subsystem before we save it in DM. By default, when you create a subsystem definition in ANSA, the contents of the subsystem are nicely organized in discrete virtual containers. So we have here the definition of the subsystem, of the body-in-white subsystem. We can see in the details tab the metadata of the subsystem, and on the right-hand side, a preview image. So this is my body-in-white subsystem, and it has its contents nicely organized in different containers. The geometry container is the one that contains the part structure of the subsystem. So all the parts that have been assigned to this subsystem are collected and organized under this geometry container. Then we have a connections container. So this is the one that collects all the connection entities and the FE representation of these connections when they are applied. So we can see here that for this particular subsystem, we have various bolts and spot welds that have been applied and have generated their FE representation. So this is a preview of the contents of the connections container. Then we have the interfaces container. This is a container that collects the various interfaces of the model. In this particular case, what we have for this subsystem is some interface points that mark either various locations of the model or in some cases, some interface properties. So some section cells, some rigid patches here in the model. So these are locations where eventually the subsystem, this body-in-white subsystem, will be connected to its neighbors. So we have here in the body-in-white at the locations that correspond to the hinges and the latch of the door subsystem, the marking of some interface properties that we will use for the assembly of this particular subsystem, the body-in-white, with the door subsystems. And finally, we have a model setup entities container that collects any other model setup entities associated with the subsystems, such as some database keywords or some set definitions or some materials and so on. A characteristic of this body-in-white subsystem that I have here is that it is a 150% model. So this means that in this particular ANSA database, I have two different configurations of parts. So if you can see here, if I rotate my model a little bit, you will see that I have both the left-hand drive variant and the right-hand drive variant of the vehicle. So as you see here, we have the mounting points for the steering wheel, both on the left and the right-hand side of the vehicle. I suppose that most of you are already familiar with part configurations. Essentially, it's a parallel structure based on some links to the parts of the original part structure that allows us to handle 150% models. So within this database, I have both the left-hand drive variant and the right-hand drive variant of the body-in-white subsystem. In the modular environment, we support such definitions and creations of multivariant subsystems. As you can see here, I have marked this subsystem with the multivariant label on the variant attribute to describe that this is a multivariant, a 150% model. And this allows us, by saving this multivariant subsystem in the DM, to have a single source of truth for all body-in-white variants, nicely organized in the DM, in one single ANSA database. Now, one of the nice things here in the modular environment is that once we activate any of the configurations, so once we convert this 150% model to a 100% model, this change and this update, so as you can see here right now, I have activated just the left-hand drive variant of my model. So I only have the steering wheel mount on the left-hand side and not on the right-hand side. So this 100% variant, the left-hand drive variant that is reflected by the active configuration, is also reflected in the subsystem attribute, so that now you can see that ANSA has automatically updated the variant attribute, and the value that it has assigned is the same as the active configuration. So if I deactivate the configuration and again switch this to a 150% model, so a multivariant subsystem, the variant attribute of the subsystem is again updated to reflect that this is a multivariant subsystem. Another key definition here on subsystem level, before I save it in DM, is the definition of numbering rules. So if I go here through the ID ranges to the numbering rules, I can see that for this particular subsystem, I have a general numbering rule in order to assign all entities to a range of IDs between 1 and 2 million through this numbering rule. And this allows me to effectively and efficiently manage my model IDs on base module level in order to ensure that all subsystems are stored in the DM with discrete ID ranges in order to ensure that there are no conflicts when the final model is assembled together. So, having prepared my subsystem in the modular environment, I can proceed to save it in DM. As we saw during the presentation, in the modular environment, we have the build process. This is a built-in process that consists of a series of actions that can be executed prior to saving the subsystem in DM in order to validate its integrity. So here we have several built-in actions for the realization of connections or generic entity builders, or for the application of numbering rules. In the modular environment, the execution of the build process can be tied, as I mentioned, with save in order to ensure that the build process is always executed when saving a subsystem in DM, and also define that any subsystem whose build process is not successfully executed will not be saved in DM. This is controlled through the modular environment settings. So if I activate my ANSA settings and I switch to the modular environment, here we have a series of settings that control the behavior of ANSA when working within the modular environment. We have several settings. In the modular architecture tab here, we can control the file type that we want to save for each model container, as well as the way that its contents will be written, whether we will save monolithic or files with references, and we can define the conflict resolution, what to do in cases of conflicts. Through the Save in DM tab, we have this Save Silently group of settings that allows ANSA to save any model containers in the DM without launching the Save in DM wizard, without waiting for user interaction. And this allows ANSA to automatically save any missing or modified contents. So any subsystems that are not already saved in DM or whose status is not up to date will also automatically be saved when the save process is triggered, according to the composition described here in the modular architecture settings. But an important definition here is these two settings here. The fact that the build actions can be automatically performed before saving a container in DM, and also that the save process can be halted in case that the build process is not successfully executed and the build status of a container is not okay. So having activated these settings in our environment, I can come here to the body in white subsystem and trigger the Save in DM function. By doing this, ANSA will first execute the build process of this subsystem, and if the build process is successfully executed, then the subsystem will be saved in DM according to the file type and the conflict resolution policy that was described in the modular environment settings. In this particular case, it will be saved as an ANSA file in DM, and in cases of conflicts, we will always spin up the iteration. So the save process has been successfully executed. You can see here that the build process was executed before saving, and it was executed successfully. So now that the build status of my body in white subsystem is okay, the multivariant body in white subsystem has been successfully saved in DM. If I activate one of the configurations, for example, the left-hand drive variant, I can switch back to the Subsystems tab and again save in DM, this time save the single variant, the left-hand drive variant of the body in white subsystem. So again, I will trigger the save in DM process. The build actions will be executed again before saving. And if they're executed successfully, the left-hand drive variant of the body-in-white subsystem will be saved in DM as an ANSA file. So you can see that the build process was again successfully executed. The build status of the left-hand drive variant of the body-in-white subsystem is okay, and the subsystem has been successfully saved in DM. We can see this from the DM update status column here, where the status of the body-in-white left-hand drive variant is up to date. Let's move to the DM browser and see what has been saved now in our DM. So we can see here that in the subsystems container of the content section of the DM browser on the left-hand drive, on the left-hand side, we now have the two subsystems, the body-in-white multivariant and the body-in-white left-hand drive variant subsystems that have been stored in DM with ANSA file type. Let's review some key characteristics of the subsystems in DM. Looking at the Details tab, selecting subsystem and looking at the Details tab, we can see the identity of the subsystem, its attributes in terms of metadata stored in the DM. So we can see here on the right-hand side also a preview image. But if we scroll down here in the Details tab, we have some very useful information. One of these is the definition family of attributes, the definition metadata. These are metadata that are filled through a process called indexing when a container is saved in DM. So essentially, ANSA, when a subsystem is saved in DM, it extracts information about the entities contained within the subsystem in terms of their IDs in order to be able and use this metadata in later stages during the model assembly. This same indexing process also keeps track in the DM of the subsystem interfaces in terms of metadata. So we can see here that the interface points and the interface properties of the body-in-white subsystem have been indexed and have been stored as metadata in the DM. For multivariant subsystems, we also have the multivariant attribute. So we can see here that for the multivariant body-in-white subsystem, this attribute has the yes value. So this is a multivariant subsystem, whereas the single variant has the is multivariant no attribute in the DM. Moreover, the build status of the subsystem that is saved in DM is also captured as metadata through the respective build status attribute. So I can see here, after saving the subsystems in DM, that in the DM browser, I can extract quite a lot of useful metadata for the stored subsystems. Another key feature here is that if I switch to the references of the subsystems that I have just saved in DM, in the lifecycle tab of the references, the relationship between the multivariant body-in-white subsystem and the single variant multivariant subsystem has been captured. So we have here a reference, and at all times, we can trace for a single variant subsystem like the left-hand drive variant, which was the multivariant subsystem that was used to generate it and store it in DM. So this lifecycle tracking between multivariant and single variant subsystems is captured in the DM browser. Now, having stored the body-in-white subsystem in DM, we can open a new database in order to review the other subsystems of our model, like the door and the glazings. So I will first open the door subsystem. So what I have here is the front left-hand drive door subsystem. We can see here the Details tab. So this is the door front left subsystem. We can see that its contents have been nicely organized in this subsystem virtual container. So we have the geometry, the interfaces, the connections, and the model setup entities, similar to what we saw earlier for the body-in-white. If we have a look at the interfaces of this subsystem, essentially what we have here is 3 interface points that mark locations, as I mentioned earlier for the body-in-white, locations on the hinges and the latch, and this is where we will perform the assembly between this door subsystem and the body-in-white subsystem. Similar to the body-in-white subsystem, we have also defined numbering rules for the door subsystem. So there is a general numbering rule that defines that its IDs should lie between the 2 and 3 million range. So again, having activated the respective settings in the modular environment, I can proceed to save this door subsystem in the DM. Again, the build process is tied with save, so the build actions will be executed. And once the build status of the subsystem is okay, then the subsystem is saved in DM as an ANSA file. We can see that the save process has completed successfully, and this door subsystem is now successfully saved in DM. So in the DM browser, I have now the two body-in-white subsystems, the multivariant, the single left-hand drive variant, and I also have my front left door. Let's open the final starting file, the final database that contains the glazing subsystem. So here we have the front windshield. So we can see for this subsystem, again, the organization of the contents in the different virtual containers. Again, for this subsystem, we have a numbering rule, a general numbering rule defining that the entities of this subsystem should lie between the 5 and 6 million range. So again, I can trigger the save option and save this subsystem in DM. Again, the build process is executed successfully, the build status is okay, and the subsystem is stored in DM as an ANSA file. So if I go now to my DM browser, I can see that I have a DM, a data repository, that is populated with the subsystems that I need in order to build my simulation model and perform the assembly. So this will be our starting point. I will start from an empty ANSA session, a new ANSA session, and we will start defining our simulation model using the subsystems that we have available in our DM. To do this, we need to select the subsystems of interest. For this webinar, I will use the left-hand drive variant of the body-in-white subsystem, the door, and the glazings. So I select the subsystems of interest, and I activate the download object definition function from the DM browser. In order to download in my ANSA session the definition of the subsystems that I want to use in my simulation model. The original model that I showed to you at the beginning of the demo had the door subsystem both on the left and the right-hand drive of the vehicle. And this is something that I want to use. So what I will do is I will use a single subsystem from my DM, the front left door, but I will create an instance of this subsystem, a definition of an instance of this subsystem in my model browser. So now I have two instances of the door subsystem, and in my simulation model, I will adapt one of the doors in order to use it on the right-hand side of the vehicle of the model. So now that I have all the subsystems definitions that I need for my simulation model, I can select them and activate the option New Simulation Model from the context menu in order to add them to a new simulation model. So if I expand here my simulation model, we will see that I have the different definitions of my subsystems under the simulation model. I can move to the Details tab and assign the attributes that I need for my simulation model. So this is my crash assembly model ID. This is my left-hand drive model variant, since it contains the left-hand drive variant of the body-in-white subsystem. I will add my project and release information. And I will also come here in the simulation model and define a numbering rule for my simulation model. So I will define a numbering rule, a general numbering rule, that any entities that are assigned directly to my simulation model will lie in the 9 to 10 million range. You can see here how easy it has been to create a subsystem definition using entities, subsystems that are already stored in my data repository. So I simply download their definitions in the model browser. I can create any instances in order to reuse any of those subsystems in different positions in my model, and I can assign them to the simulation model, ensuring that the model that I want to assemble and save in DM has the correct contents. Now, the next step here is to review this attribute, this IO index attribute. This is a characteristic of the subsystems assigned to the simulation model. It can be found under the adapting attributes family of metadata in the details tab. So under the DM category, we have the IO index. This IO index attribute controls the order in which the different references to these subsystems will be written in the main keyword file of my simulation model. So essentially here, if I make one small change, what we have here is that by specifying the IO index as in this particular order, in the solver file of the simulation model that I will save in DM, first I will have an include reference to the body in white, then I will have two include references to the two door instances, and finally I will have a reference and include reference to the glazing subsystem. The next step here is to control and adapt one of the two door instances in order to use it in this simulation model on the right-hand side of the vehicle. When I started saving my subsystems in DM, I saved them having applied some numbering rules in order to ensure that they will have discrete IDs. So the body in white has been stored in the DM in the 1 to 2 million range, the door subsystem is between 2 and 3 million, and the glazing subsystem is between 5 and 6 million. However, since I have two instances of the door subsystem, I expect to have some classes of IDs if both of them are loaded in my model. To avoid this, I can control the IDs of one of the subsystem instances on simulation model level. This is done through the ID ranges, the target ID ranges function. So if I select the door subsystem instance that I want to adapt, I can select the target ID ranges option and specify a new target of IDs for this particular subsystem instance in this simulation model. So I will move this to the 3 to 4 million range to ensure that there is no conflict with any of the other subsystems. And I will press OK. This is reflected again on the adapting attributes of this particular subsystem instance under this simulation model. So if I go to the adapting attributes again, under the user group of attributes, you can see that this subsystem has some target ID ranges when used in this particular simulation model. So the target ID ranges is between the 3 and 4 million range. These target IDs, together with the definition attributes, the definition IDs of this subsystem in DM, will be used by ANSA in order to calculate the required offsets that will be used when this subsystem instance is referenced in the simulation model. Apart from the ID ranges for this subsystem instance, I need to also adapt the position. So in order to use this subsystem instance on the right-hand side of the model, I need to adapt its position. So I can select it and activate the context menu option, Actions, Position, Define Transformation, in order to define a transformation, a mirror transformation for this subsystem. The first thing that one could notice in the Define Transformation card is that the ID of the transformation lies within the ID ranges that I have defined for my simulation model. If you remember at the beginning when I created the definition of this simulation model, I defined the numbering rule so that all the entities that are contained directly within the simulation model lie between the 9 and 10 million range. So I can create here my mirror transformation. I can define the plane, the mirror plane, apply the transformation and press OK. This transformation action is again reflected in the adapting attributes of this door subsystem instance. So if I scroll down, you can see here that now an auto-created transformation file is stored as an adapting attribute for this subsystem instance. This means that when I build and save this simulation model in DM, this particular instance of the door subsystem will have its IDs transformed in order to lie between the 3 and 4 million range, but also its position will be adapted in order to use it on the right-hand side of the model. So, having created the definition of my simulation model and adapted its contents, I can proceed to the actual assembly of the various base modules of the various subsystems. Now, between the body in white and the door subsystems, I will use ANSA connector entities on their interfaces in order to assemble them together. Normally, this action only requires me to load the interface representation of these subsystems from the DM. So I would have to just select the subsystems of interest and from the DM actions, load the interface representation. However, between the body in white and the glazing subsystem, what I will do for this model is that I'm going to join them, I'm going to connect them using some adhesive lines. In order to generate the connecting elements of the adhesive lines, I need to load the full representation of the body in white and the glazing subsystems. So, in order to proceed with my assembly, I will select my simulation model and actually load its contents, load the full representation of the subsystems at this stage. So by pressing the load button on the simulation model, the various subsystems contained in this simulation model will be loaded in the existing ANSA session. So the body in white, the two instances of the door subsystems, and the glazing subsystem will be loaded, their full representations will be loaded in the ANSA session. Moreover, having defined the adaptation of one of the two instances, I expect that one of the door subsystems will be renumbered, its contents will be renumbered, but also its position will be adapted so that it is used on the right-hand side of the model. So let's wait for ANSA to finish loading and we can review our model. Okay, I will switch to subsystem draw mode here. So we can see that the left-hand drive, the left-hand side front left door subsystem has been loaded. The body in white subsystem has been loaded. The glazing subsystem has been loaded. And on the right-hand side of the vehicle, we also have another instance of the front left door subsystem adapted in order to be reused on the right-hand side of the vehicle. If we have a look at the interfaces, we can see here that the interfaces of the two door instances have been loaded once on the left-hand side of the model and once on the right-hand side of the model. So these are the locations where we will perform the assembly between the subsystem, the door subsystems, and the body in white subsystem. On the other hand, between the body in white and the glazing subsystems, we need to use some adhesive lines. So what I can do is I can input these connections in the form of an XML file. And once I input them in my model, we can see that these are the connections that have been input from the XML file in order to connect the body in white subsystem and the glazing subsystem. I can pick these connections and add them to a new subsystem. In this case, ANSA automatically creates a connecting subsystem. You can detect that this is a connecting subsystem both through the characteristic icon, which differs from the regular subsystems, but also from the subtype attribute of this subsystem, which is connecting. I can come to the Details tab and provide the correct metadata. So I will name this my Connections subsystem. I will add the project and release metadata and also my target representation. I will also define a numbering rule for this subsystem, a general numbering rule so that all its contents lie between the 6 and 7 million range. In order to ensure that no conflicts will exist between the contents of the connecting subsystem and the contents of the other subsystems in the simulation model. I can also open here the Connections tab in the model browser in order to review the connections that have been assigned to this connecting subsystem. So within the model browser, I have a view similar to the connection manager. I can see that these are the 7 adhesive lines that I have assigned to my connecting subsystem. I can expand here the right-hand side panel so I can pick them and assign from here the target FE representation. Let's use a hexa contact FE representation for this use case, and I will create also a single contact. So I have defined the FE representation settings for my subsystem. I have defined the numbering rules. So the next step is to actually build this connecting subsystem in order to realize the connections and also renumber the entities to the target numbering ID ranges. So before I do that, I will pick this connecting subsystem, the connections connecting subsystem, and drag and drop it onto the existing simulation model definition. So now my simulation model contains not only the regular subsystems, but also a connecting subsystem that holds the adhesive lines that connect the glazings and the body-in-white subsystem. So back to the Subsystems tab, if I activate the build process of this connection subsystem, we will see that the connections will be realized and the generated FE representation, so the hexa elements, the solid elements, and the contact definition have been added to the subsystem contents. If you wish, you can rename also this contact. So I can rename this to adhesive contact just to be a characteristic identifier of the contacts for these adhesive lines. So now I have a simulation model that contains the regular subsystem and the connecting subsystem that holds the ANSA connection entities, the adhesive lines, but also the generated contact and elements that connect the glazings and the body-in-white subsystem. The next step here is to perform the assembly of the model between the body-in-white and the door subsystems. For this, we can make use of the subsystem interfaces, the body-in-white and the door subsystems interfaces, and try to automatically define connectors on the simulation model level. So we can do this by activating the actions create connectors option from the simulation model context menu. So a wizard that assists in the generation of connectors from pairs of assembly points opens up. So I can specify here the desired proximity and the desired target representation. In this case, I want to use constrained rigid bodies. I will press OK. So ANSA detects pairs of assembly points that belong to different subsystems that are assigned to this particular simulation model within the predefined proximity and generate some connector entities. So we can see here that 6 connector entities have been created between the body-in-white and the door subsystems. And they have been assigned to the simulation model under the virtual container connectors. If we review these connector entities that have been generated, there are 6 of them, 3 on each side, connecting the door subsystem and the body-in-white at the hinges locations and at the latch. I can convert this connector's virtual container to a connecting subsystem. So another connecting subsystem in the simulation model that will hold the connector entities between the body-in-white subsystems, the body-in-white and the door subsystems. So back to the subsystems tab, in the details tab, I can provide some more characteristic attributes for this subsystem in the details tab. So I will name this patches. I can provide my project and release metadata, and also the representation of the subsystem. I can also specify a numbering rule. So I will add a general numbering rule for the entities that belong to this subsystem between the 7 and 8 million range. Again, to avoid any ID conflicts with the other subsystems that belong to the simulation model. So once this is done, I can also build this patches connecting subsystem in order to execute the different build actions, which will realize the connector entities that are assigned to the subsystem, and it will also renumber all the contents of the subsystem to the desired numbering range between the 7 and 8 million. So you can see here on the left-hand side that now my connectors have been applied. Their contents have been renumbered between the 7 and 8 million range, and I have generated constrained rigid bodies between the patches that exist at the front on the door hinges and at the back on the latch location. So the next step is to actually proceed to build and save the simulation model in the DM. Before I trigger the save action, I would like to remind you of a few things. So in my modular environment settings, I have specified that I want to automatically save any missing or modified contents before, as part of the save process, and also I want to execute the build process automatically on save, and I want to block the saving if the build process is not successfully executed. If I now trigger the save in DM process on the simulation model, a series of actions will be performed by ANSA. So first, the build process is executed. Once the build process is successfully executed for all subsystems, ANSA will detect that the connections and the patches connecting subsystems have not been saved in DM already. So the first save action that will be performed is to actually save the connections and the patches connecting subsystems as ANSA files in my DM. The next step, once these ANSA files have been generated for the connections and the patches connecting subsystems, is to proceed and save the simulation model in the DM. For the simulation model in the modular environment settings that I have applied, I have defined that I want it to be saved in DM as a solver file with references. This means that all of its subsystems will have to be saved in DM as solver files so that the simulation model can be written as a keyword file with references to the includes of the subsystems. This means that while I'm working in the modular environment, I'm working primarily with ANSA files. I store the ANSA subsystems of interest in the DM. And when it's time to require the solver representation of these subsystems in order to save a simulation model, ANSA will automatically generate the solver files, the solver includes for these subsystems, using the ANSA definition files. Okay. So all these actions are executed sequentially by ANSA. So the various missing subsystems are saved. And then once these subsystems are saved as solver files in the DM, eventually the simulation model will also be saved as a DEC file, as a solver file with references. Okay. All these actions can be seen in the terminal in the background while ANSA is working. So eventually, once the save process is finished, one could also expand the ANSA info window to review the sequence of actions that have been performed So the different build processes, the generation of the solver representations for the various subsystems, and eventually the writing of the simulation model solver file are all logged in the ANSA info window and the DM log. So this simulation model is now saved in DM as the first iteration of my simulation model, containing references to the solver files, to the includes of the contained subsystems, and these references are written in the main file of the simulation model in the order defined with the IO index adapting attribute. So if I select this subsystem and this simulation model and text edit its keyword file, we will see that we have a block of comments here at the top called the DM header that defines the identity and the type of this particular model container. So we can see that this is a simulation model and we can see its metadata. And then if we move further down, we have some include references to the various subsystems. So first we have an include reference to the body in white subsystem. Then we have an include reference to the unadapted door subsystem, which is used in its original position with the original IDs, followed by a reference, an include reference to an adapted file for the door subsystem, the one that has the transformed IDs and position in order to use the same subsystem as an instance on the right-hand side of the model, the glazing subsystem, the connections, and the patches, the two connecting subsystems at the end. This automatically generated solver include for the adapted subsystem, if I select the adapted subsystem instance in the model browser and text edit its solver file in the DM, we can see that this is the adapted subsystem that is automatically generated and stored by ANSA and referenced in the simulation model, which contains the transformation keyword and an include transform reference to the original unadapted door subsystem. So we can see here that we have the mirror transformation in order to adapt the position and the ID offsets that have been automatically calculated by ANSA based on the target ID ranges, which was in the 3 to 4 million, and the source definition ranges, which were between the 2 and 3 million. So an offset of 1 million was automatically calculated by ANSA in order to use this subsystem in the simulation model in a different position with different IDs. Back to ANSA, if we go to the DM browser, there are several things we can see. So the first thing is that the simulation model has been saved in DM, and we can see here the hierarchy, so the different contents of the simulation model. It contains the body in white, two instances of the door subsystems, the glazings, and two connecting subsystems. If we go to the subsystems tab, we can see here that several subsystem files now exist in the DM. We have the ANSA files for all the subsystems, the body in white, we have the original multivariant, but also the left-hand drive single variant. We have the door front left subsystem. We have the glazings and the two connecting subsystem. And then we also have the solver files that were automatically generated during the saving of the simulation model. Some interesting things here is that we can see is, first of all, if we select, for example, the ANSA file of the body in white subsystem, we can see here that in the references tab, in the life cycle, we have now a new reference that was automatically captured as metadata in the system. And this is the reference between the ANSA file of the body in white and the automatically generated solver file, the solver representation that is used in the simulation model. If I select the LSDyna file type of this body in white subsystem, we can see in the references that there is a reference to the ANSA representation, so the ANSA file of this body in white subsystem. So at all times in the DM, we have this relationship between the solver files and the ANSA definition files that we can later use for the creation of new iterations. In the Where Used tab of the references, we can see that this solver file of the body-in-white subsystem is used in a simulation model. So here we can see all the containers that use the solver files that we store in our DM. If we go to the door subsystem, in the life cycle, we can see here that we have the solver representation. But also, if I select the solver file, we can see that there are two links. One of them is the ANSA representation, so the reference between the solver file of this LSDyna keyword file for the door subsystem. So we have the relationship between the ANSA file and the solver file, but we also have another link that is captured with type adaptation. So what we can see here is that this particular subsystem that is stored in DM has also generated an adapted representation for this subsystem. So we can see this here through the links, and we can open this in a new tab. So eventually here what we have is the adapted representation of this door subsystem. And of course, if we text edit it, we will see that the solver file is the one that was automatically generated by ANSA, holding the transformation keywords for the original door subsystem. So as you can understand, through this automatic generation of adaptation keywords and adapted subsystems in the DM, we have more efficient storage management because we can reuse the original subsystems that we store in DM, adapted in different positions in the different models, and ANSA only stores a smaller keyword file, so it doesn't write several copies of the same subsystems in the DM. It uses a transformation keywords in order to store, to effectively handle the storage space. Another very interesting thing to review here in the DM browser is if we select this connections connecting subsystem, the solver file of this connecting subsystem, and we switch to the other links tab, we will see that we have some intermodular connectivity links. So these are some references that are maintained in the system, in the data manager, and they evaluate essentially the compatibility of the regular subsystems that exist in the DM with the connecting subsystem. So what we can see here is that the body-in-white and the glazing subsystems with iteration 1 are connected and are compatible with this particular connecting subsystem. This means that this connecting subsystem that I have selected here can be used with these two regular subsystems without having to realize the connections again. The solver file that exists can be used as is. So with this, we have stored in our system, in our DM, the first iteration of a simulation model. So now let's assume that we have started our simulation activity. We have performed some simulations with runs that use this particular simulation model. And we have noticed some irregularities, some abnormalities in the results. And we want to modify some of the contents of this simulation model in order to submit new iterations of the runs to the solver. The way to start working with iterations in ANSA, so assuming that I'm a user that wants to start creating iterations, I have to launch the DM browser, identify the simulation model of interest and its contents, and eventually start creating iterations of the subsystems of interest. So, for example, I want to work with a body-in-white and I want to introduce some modifications in order to improve, let's say, the front crash performance of this simulation model. So I can select the solver file of the body-in-white subsystem that is used in this particular simulation model of interest and start the creation of new iterations. So I can invoke the next iteration function from the DM browser. Through the references that are maintained in the system between the solver file and the ANSA definition file of this body-in-white subsystem, the ANSA file of the subsystem will be loaded in the ANSA session. So I can use this ANSA subsystem file that is loaded here. Let me switch to PID mode. So I have here in my subsystems the ANSA file type of the body in white that was loaded through the next iteration action on the solver file in the DM. And let's say that I want to modify some properties. So I want to improve the firewall intrusion. So I can go to the contents. I can come here to the properties of my subsystem. And I want to pick some properties from my model. So let's say that I want to pick the properties of these front rails. And increase their thickness. Okay. So this one here as well that I want to pick. Okay. So I can come here and I can modify the thickness. Let's say that I want to introduce a 10% thickness increase. So modify the thickness values. This modification of the property thickness marks my body in white subsystem with the magenta DM update status. This means that my subsystem is now modified compared to the subsystem that exists in the DM. Normally, in the past, actually, if you wanted to, let me remove the highlight here. So in the past, if you wanted to keep track of this modification when you save a new iteration of this body in white subsystem in the DM, you would expect your users to go to the details tab and fill in a comment. This comment could also be mandatory for the save. This can be controlled through the modular environment settings, so you can force your users to add the comment when saving new iterations. But in ANSA, in the last couple of versions, we have introduced the change set management functionality, which can be activated from the ANSA settings. So from the model browser settings, you can activate the change set management functionality. And once you do this, any modifications that you perform on your subsystems are registered, are tracked. So these create an ANSA entity called the change set. So all the actions that I have taken are triggered, are captured here. Some of the actions that may be relevant or you don't want to include in your change set, you can delete. So you have some nice management of the functionality here. But what you can do is provide a relevant summary. So for example, improve firewall intrusion, for example. Okay. And then I could also provide, if I wanted some more information, 10% increase of rails thickness, for example. Okay, so you can provide a relevant summary. So you have here a detailed list of actions that provide you information about the entity that was modified, the modification that took place. So you can see here that for some properties, I can see that I have edited the thickness and I have the starting value and the final value. I have a timestamp, so I have here information on who performed the change and when through the user and the timestamp attributes. And on the right-hand side, we also have a snapshot of the change set. So the model is transparent and only the areas where the modifications took place are highlighted in this change set image. Okay. So performing such a modifications and having the change set management functionality active, when I save in DM this body in white subsystem, and remember I have the silent save active, the silent save settings active, which means that the build process will be automatically executed to validate the integrity of the subsystem. And then in cases of conflicts, a new iteration will be stored for my subsystem in DM as an ANSA file. So I activate the save function, the build process is executed, it applies any numbering rules or it realizes any connections or generic entity builders, and then it saves the subsystem in DM, and in case of conflicts, it spins up the iteration. So now I have the second iteration of the body in white subsystem in DM. So I have introduced a change in my subsystem aimed at improving the performance of my model in the simulation. So now if I go to the DM browser, I can see that the second iteration of the body in white subsystem has been stored. I can see that in the references, in the life cycle, apart from the history link between iteration 1 and iteration 2, and the relationship between them captured through the history reference, we also have a reference with a change set object. And so by selecting the change set object, we can have a quick preview of the summary and the snapshot. And then in the DM browser, if we switch to the change set tab, we have here all the information about the modifications that took place when saving this second iteration of the subsystem in the DM. So all the modifications are captured. I know who introduced the change, when, and what was the change that was introduced when saving this second iteration in the DM. So now it's time to proceed and save my simulation model as a new iteration in the DM. So I have to select the existing simulation model and trigger the iteration function in order to download in my ANSA session the definition of the simulation model. So I have here the simulation model definition and its contents, and I can identify that I have updates for the body-in-white subsystem. I can switch to the DM tab, identify my updates, and simply right-click and replace the metadata, replace the currently used attributes. Doing so, I update my simulation model definition and now include a reference to the second iteration of the body-in-white subsystem. This action marks my simulation model as modified because now I have updated its contents. This means that I need to build and save the simulation model in DM. One thing that we need to check here is that we have a new iteration of the body-in-white subsystem with a change that I performed at the rails at the front. And now we have two connecting subsystems. So ANSA would need to evaluate the compatibility of these connecting subsystems in order to determine whether they can be reused as is or not. For the Apache subsystem with the connectors, simply loading the interface representation would do because the connectors are searching for assembly points, so the interfaces can be loaded and the connectors contained in the Apache subsystem can be evaluated and, if needed, reapplied. But for the adhesive lines in the connection subsystem, things are a bit more complex. So if you remember, when I saved the first iteration of the simulation model in the DM, the connection subsystem had some references with the first iteration of the two subsystems of the body-in-white subsystem and the glazing subsystem. Now that I have a second iteration of the body-in-white subsystem stored in DM, when I save this body-in-white subsystem in my data manager, ANSA automatically evaluated the compatibility of this new iteration with the existing solver file of my connections subsystem. This means that ANSA has determined that the change that I introduced in the body-in-white does not affect the FE representation of the adhesive lines contained within the connection subsystem, and there is no need to reapply the connections. I can reuse the solver file that I already have in the DM since they are compatible. This means that when I build and save my simulation model, there is no need to load the full representation of the body-in-white and the glazing subsystems in order to realize the connections again. So on build, only the interface representation of the regular subsystems and the full representation of the connecting subsystems is loaded. The build actions are executed successfully. My simulation model now has build status OK and can be saved in DM. And I can see that all the contents, all the subsystems contained within the simulation model can be used as is from the DM. So I will save the simulation model as a new solver file with references in the DM. This will be the second iteration of the simulation model that will contain the second iteration of the body-in-white, but it will reuse all the existing subsystems with iteration 1 that I have for the doors, the glazings, and the two connecting subsystems. So right now, ANSA first generates the solver file for the second iteration of the body-in-white subsystem, since I had only saved it as an ANSA file. And once this is saved, it will then proceed to save the simulation model as a keyword file with references. I can trace through the terminal or the ANSA info window the action that is performed by ANSA, and eventually I can text edit this simulation model, the new version of the simulation model. I can see that it has iteration 2, and I can see here that it references the second iteration of the body-in-white subsystem, but other than that, it has reused all the existing includes from the first iteration. So there was no need to generate new connecting files or new regular subsystem files. If we go back to ANSA, to the DM browser, we can see here in our simulation models that we now have a second iteration stored in the DM. It has a lifecycle link with the first iteration, so it was created using the first iteration of the model with some modification. And in my subsystems, I have the second iteration of the body-in-white stored as an LS-DYNA file. So we can see here the relationship and the ANSA representation. We can see that this is used in the second iteration of the simulation model. On the other hand, if I pick the solver file of the DOOR subsystem, I can see here that this first iteration of the DOOR subsystem is used in both the first and the second iteration of my simulation model. Now, let's assume that I want to perform another modification in the body-in-white. So I will pick again now the second iteration of this body-in-white subsystem. So I'm an analyst working with this simulation model, and then I want to introduce some new modification in my model. So I trigger the next iteration action on the body-in-white subsystem, the second iteration of the body-in-white subsystem, and this time I will introduce a change in one of the areas that would be affected by that would affect the intermodular connections. So for those adhesive lines here between the body-in-white and the DOOR subsystem and the glazing subsystem, I will pick one of the properties. So let's switch to the Contents tab and get the properties of this subsystem. And this time I want to pick this dash panel here and update its thickness. So I will increase this from 0.75 to 1. And I can see that this action marks my subsystem as modified. Something has changed in its content, so I need to save it in DM. I can go to my change set tab and review here the change that was introduced. So I can add some summary, for example, modified dash panel thickness, and trigger the save action. So again, the build process is executed, and then this subsystem will be saved in DM as a third iteration of the body-in-white subsystem as an ANSA file with iteration 3. So I can see here on my change set that the respective area where the modification was introduced is highlighted. So this subsystem, once it is stored in DM with the third iteration, we can go to the DM browser and review both the references in terms of life cycle. So we can come here and see that the third iteration of this body-in-white ANSA file has been stored in DM. It has a previous version and a change set. I can review the changes, so always keep track of who introduced the modification when and what was this modification. But we also see here that in the references in the other links, this third iteration of the body-in-white has been evaluated as incompatible with the existing iteration of the connections connecting subsystem. So ANSA evaluated this new iteration of the body-in-white and determined that the modification that I introduced means that the existing connecting subsystem cannot be reused as is. This modification of the thickness here on the dash panel that I introduced will affect the hexa elements of the connection FE representation. This means that these connections would need to be realized again in order to generate a new solver file for the connecting subsystem. So if I were to proceed to perform the next iteration of this simulation model, the definition file of the simulation model will be loaded, the model browser I need, in the model browser. This time, I identify that there is an update for my body-in-white subsystem. I can identify and replace its attributes in the simulation model definition. Again, you see that the simulation model is marked as modified. So now if I proceed to build my simulation model in order to save it in DM, we will see that the incompatibility of the body-in-white subsystem with the existing connections file, the existing connecting subsystem with the adhesive lines, means that the body-in-white subsystem and the glazing subsystems that are associated with these connections connecting subsystem need to be fully loaded as a full representation in order to be able and realize the connections, the adhesive lines again, in order to produce a new solver file for this connecting subsystem. So this is what ANSA does right now. For the door subsystems that are not related to the connecting subsystem, there is no need to load the full representation. So those are only loaded as an interface representation, whereas the body-in-white and the glazing subsystem will be loaded as a full representation. So you can see here that indeed the doors are not loaded, but the body-in-white and the glazing subsystems have been loaded. The build actions were successfully executed. The connections in the connecting subsystem were realized successfully as part of the build process, but we see that this new realization of the connections marks the existing connecting subsystem as modified. This means that this connecting subsystem needs to be saved as a new iteration in the DM, and then a new solver file will have to be generated in order to be referenced by the new iteration of the simulation model. So I will now pick my simulation model and save it in DM. So this will automatically trigger the save in DM process. Any missing or modified contents will first be saved in DM. So this means that the connections connecting subsystem first will be saved as a new iteration in the DM. And then the solver file for the new iteration of the connections connecting subsystem and for the third iteration of the body-in-white will be saved as solver files, as a solver includes in the DM, in order to be referenced by the third iteration of the simulation model. So ANSA on the background is performing all those save actions silently without any need for user interaction. And eventually, when the simulation model is saved in DM, we will edit its text file in order to see that it is now referencing. So the third iteration of the simulation model is referencing the third iteration of the body-in-white. It has reused the first iteration of the door subsystem and the adapted door subsystem on the right-hand side. It has reused the first iteration of the glazing subsystem, but now it has referenced the second iteration of the connections connecting subsystem, which was modified due to the change that we introduced in the third iteration of the body-in-white subsystem. As for the patches, the connecting subsystem between the body-in-white and the door, the original first iteration is again reused. Now, let's review one final use case. Let's assume that, again, I'm working with this simulation model, and I want to introduce another change in the body-in-white subsystem. So I will pick this third iteration of the body-in-white and perform the next iteration action. This will load the ANSA definition file of the third iteration of the body-in-white subsystem. And this time, I will introduce a change in the materials of my model. So a change that would theoretically affect the areas where the body-in-white and the glazing subsystems are connected to each other, but it is a change that should not affect the existing connecting subsystem. So if I pick here these materials, so the materials that I use in my model, and let's say that I modify the Young's modulus. So in my model browser, this action has marked my subsystem as modified. And in the Change Set tab, I see this modification here. So again, there is tracing of who performed the modification when and what was this modification. So let's say that I updated the model materials and save this subsystem as a new iteration in the DM. Again, you know the sequence by now. The build process is executed in order to validate the integrity of this subsystem. And then this subsystem is saved in DM according to the modular environment settings as a new iteration ANSA file. So I will have now in my DM browser, when the save process is completed, the fourth iteration of the body-in-white subsystem in DM. Once this fourth iteration is stored, I can review this in the DM browser. So now we have the fourth iteration of the body-in-white subsystem in DM. We have here the lifecycle reference with the previous version, and in the other links, when this iteration was saved in DM, ANSA has evaluated that with the second version, the second iteration of the connections connecting subsystem, this body-in-white fourth iteration is compatible. So the change that we introduced here with the materials does not affect the second iteration of the connecting subsystem that we generated earlier. So we could reuse this as is. So this means that if I perform the next iteration action on the third iteration of the simulation model, and I download the definition in my model browser, I can update the metadata of the body-in-white subsystem and then trigger the build process for this new simulation model iteration. And this time, due to the compatibility of the fourth iteration of the body-in-white subsystem with my simulation model, ANSA will not have to load the full representation of the subsystem. It will need just to load the interface representations to validate the assembly and eventually save the simulation model in DM. So we have the definition of the simulation model. We can go to the DM tab and get the fourth iteration of the body-in-white subsystem and replace the attributes. So again, the simulation model is marked as modified. I can trigger the build process. If you remember, this fourth iteration is compatible with the second iteration of the connections connecting subsystem, which means that during the build process, only the interfaces are loaded in order to validate the assembly. And then I can proceed to save this in DM as a new solver file with references. So eventually I will have a fourth simulation model iteration stored in my DM that will reference the fourth iteration of the body-in-white subsystem and the second iteration of the connecting subsystem, while it will reuse the first iteration of the doors, the glazings, and the patches subsystems. So when the save process is finished, we can review in the DM browser the outcome of our save process. So if I text edit this simulation model in DM, just to validate that this is the fourth iteration that uses the fourth iteration of the body-in-white subsystem, the second iteration of the connections connecting subsystem, and then the two door instances, the glazing subsystem, and the original patches connecting subsystem. So back to ANSA, let's go to the DM browser. So you can see here that now we have 4 simulation models stored in the DM. We could view here for my simulation model the life cycle. So we can see here that we have a chain of 4 simulation models in this history graph. So we can see the evolution of the model from the first to the second, the third, and the fourth iteration. Of course, this can be reviewed also through the references tab at the bottom. So we can see here the different reference relationships between the different iterations of the simulation model. Switching to the subsystems tab, we have here the various subsystems that we have stored in our DM. So for example, if I pick the door subsystem, I can see here in the references that is used in 4 different simulation models, and I can have information about each of these models by selecting and viewing the metadata on the right-hand side. We have the life cycle references here, but we could also see this information in a graphical representation. So I could open the where used references graph in order to review that this particular subsystem is used in 4 different simulation models. So I can see here the relationships. Going back to the subsystems, I can pick, for example, the 4th iteration of the body-in-white subsystem, the LS-DYNA. I can see here that this is used only in 1 simulation model. In terms of life cycle, we can see that it has a representation, an ANSA representation, so that there is a reference between the ANSA file and the solver file. If I open the life cycle graph of this particular subsystem, we can see here that this is on the right-hand side here on this additional node, the solver representation. So this is the LS-DYNA subsystem for the body-in-white with iteration 2. It is linked with the 4th iteration of the ANSA file, and the ANSA file is linked with a history link with the 3rd iteration of the body-in-white subsystem. Here in this life cycle graph, we have lots of navigation capabilities, so we could navigate the different relationships using the various arrows or connecting lines that are displayed on each subsystem node, or we could use the navigation panel on the right-hand side. So for example, by selecting this 3rd iteration of the subsystem, I can show the previous version. So I could show that it is also linked with the 2nd iteration, or I could select to show the roots. So I could select to open here in this life cycle graph all the life cycle history of these subsystems. So what we see here is that the body-in-white subsystem in its life cycle has gone through the evolution, the different stages. So it has gone from the 1st to the 2nd, the 3rd, and the 4th iteration. We can see here that each of these subsystems also has solver representation files that I can view either with the navigation pane on the right-hand side, as I mentioned, all, or using the respective buttons here in the life cycle graph. I can close the ones that I'm not interested in. And it is also possible to view, apart from the history and the solver and ANSA file relationships, relationship between different variants. So if you remember this body-in-white subsystem, the left-hand side, the left-hand drive variant of the body-in-white subsystem was generated from the multivariant body-in-white subsystem, and this relationship is captured in this life cycle graph here. So through the life cycle graph here, we can have information about the evolution of the different subsystems. We can also have information about the change set in this view. So by selecting any of these nodes and moving to the change set tab, you can see here the change set of each of those iterations in respect to its parent. So we can see that from the 1st to the 2nd iteration, we had modified the thickness of the rails. Between the 2nd and the 3rd iteration, we had modified the property thickness of this dash panel. And between the 3rd and the 4th iteration, we had modified the materials of the model. A very nice feature here is that you can view this change set history collectively by selecting any 2 iterations of interest. So let's assume that I select the 1st and the 4th iteration of the body-in-white subsystem, and I can activate the context menu and use the option Show Change Set History in order to review all the change set history of the 2 iterations. So I can see here that the various change sets between the different iterations are grouped within a new tab at the bottom of the DM browser. So I can see here that I have the change set history of the body-in-white subsystem from iteration 1 to iteration 4, and each of those change sets are listed as separate objects here in this list of actions. So I have the first change set between iteration 1 and 2, and I can review the changes. I can see who was the user, when was the modification introduced, and what changed. I could pick another change set and view here the information, and respectively pick the other change set. So all these objects are grouped, so we have a nice change log here, and we have a nice view of the actions for each of those change sets. In order to review this life cycle of our models here, apart from the change set functionality that we have here, we can go back to the simulation models and perform some comparisons. So for example, let's assume that I want to see what are the differences between the first and the fourth iteration of the simulation model. I can select them, and from the context menu, activate the option Compare Containers. So this opens a new tab in the model browser, in the DM browser. It opens this Compare Containers tab, where the two simulation models are opened in a new tab, and they are compared both in terms of their metadata, but also in terms of their contents. So we can see here that there are differences in the properties of these two simulation models. So one has iteration 1 and the other one has iteration 4. But we can also see that there are differences in the contents. So we can see that there are differences in the body-in-white subsystem and the connections connecting subsystem. And if we expand these, we can see that the first iteration of the simulation model is using the first iteration of the body-in-white, while the fourth iteration of the simulation model is using the fourth iteration of the body-in-white. And if we move to the connections connecting subsystem, we can see that one model uses the first iteration of the connecting subsystem, while the other model uses the second iteration of the connecting subsystem. So through the compare containers functionality, we can easily review two models and understand what has changed between the two in terms of their contents and their metadata. You can tune here the diffing settings. So there is a respective button here that you can use in order to control which of the attributes will be used in the comparison in order to filter out any, let's say, unneeded attributes. And eventually, the result of the comparison can be also seen through the diffing indicator. So any entities that are the same are marked, according to the settings, are marked with a green indicator, whereas wherever you have diffs, you have this orange diffing indicator. Of course, I mentioned this because some of the attributes may not be of such importance in order to mark some metadata as different. So for example, here we have some dates. Of course, between two different iterations, you would have different dates. So you could remove the dates, for example, for the comparison, and eventually see that there is no differences in terms of attributes for these two simulation models. But anyway, once you identify differences in the contents of two simulation models, you could also invoke, if you wanted, the compare tool in order to understand what has changed in the actual model. Maybe there is changes in the geometry, maybe there are changes in properties or materials. So, for example, here in this example, if I select the body-in-white used in the two different iterations of my simulation models, I could invoke the compare tool. So doing so, the two subsystem files will be loaded in two separate ANSA models in order to invoke the compare tool and perform a comparison between the two. So eventually, the compare tool settings will open up here in the ANSA session so that I can control what will be the settings for my comparison. And then once I compare the two models, I will be able to review them within the ANSA session. Of course, since we're talking about the body-in-white, this takes some time now to load the models. But once the models are loaded, we will see the compare tool settings. So just give me a couple of seconds and I'll demonstrate this for you. Now, in the meantime, while this is loading, I can also open a new ANSA session to demonstrate to you one final feature. Here are the comparison settings. So let's say that I only want to compare my model in terms of the geometry. So I can press OK in order to proceed with the comparison. But in parallel, let me also open another ANSA session so that I can show you the final feature here. So while the models are loading and my ANSA session is loading, I would like to inform you that we are at the very end of the webinar. So in a couple of minutes, we can take some questions and see if you have any queries regarding the webinar topics. Now, let's while the comparison is loading, let me go back to the DM browser and show you the final feature in parallel. So for my simulation models, we also have some detailed reporting capabilities. So what we have done is we have developed a script, a custom script that can be used in order to have a user-defined action in the DM browser. This can be controlled through the DM configuration settings. So you need a file called dmviews.xml, and you can specify here in the ANSA settings in the DM browser where is the DM configuration folder. So essentially what you need there is this dmviews.xml file and the script that will be used. So essentially you need two files, an XML file in order to define the custom action and the script that will be executed. This script, the DM object report script, is already available in the distribution package of ANSA. So you could find this under the scripts DM directory of your installation. And having defined that, you could activate this custom action, the create report, that triggers the execution of a script. And this essentially requires that you select a destination for the report. So for example, let's say that I pick this folder. And the script will generate, it will collect information about the selected object in the DM in terms of its identity, its metadata, its relationships, its differences to the parents or any descendants, and it will generate a PowerPoint report. So while the report is generating, I can switch back here to the previous session where I have invoked the comparison of the body-in-white subsystem. So I could see here what are the differences between the first and the fourth iteration of the body-in-white subsystem. So I could see here that there are some changes in the properties. So these are the changes that I introduced at the rails and at this dash panel. But also if I view my materials, there are also some differences in terms of the model materials. So I can see that the material of several entities in the body-in-white has changed. Let me close the compare tool here and let me open the report that has been generated for the simulation model. So let me navigate to my file system and fetch this report for you. Okay. Sorry, I've opened the wrong report. This is the report that I want. It's not this one. Sorry. Okay. So I'll show you the report. So this is the report that I generated for the third iteration of the simulation model today. So essentially what we have in this DM report is an overview page with some generic information about the object for which the report was generated, a summary page where we have information about the model. We have some hyperlinks here that point to the different attributes that we have extracted for this object from the DM. So these are hyperlinks that you can use to navigate to the different pages of the report. We have information about the contents. Okay. We also have information about the life cycle of the simulation model. We can see that it has 2 previous versions and 1 next version. Okay, and we also have a change log to see what has changed. So we can see here that compared to the second iteration, this particular simulation model uses the 3rd iteration of the body-in-white and the 2nd iteration of the connecting subsystem, whereas its parent was using the 2nd iteration of the body-in-white and the 1st iteration of the connecting subsystem. With that, I have concluded the demonstration.